So, we will continue our discussion about the density of states. So, what we have seen that density of states, this expression we got, if we plot. So, this the plot, and below Fermi level all states are filled, So, now I was discussing if temperature is not 0. So, then what will happen? What about the density of states? So, at finite temperature, so density of states, it is basically whatever density of states. So, that is there. Now, that will be modified with the Fermi Dirac probability. Since its value is 1 to 0, its value is 1 to 0. Okay. So, if I multiply with this function, so this function for temperature T equal to 0, it is 1, right. It is 1 when E is less than EF, when E is greater than EF. So, that is 0. Okay. So, there will not be any density of states, because density of states, it's we are telling in terms of basically energy levels, but energy levels will be there. Since here I am telling it will be 0. So, that means here, so whatever density of states, that is equal to the density of electrons. As I told, this n we have considered in both way. Each electron will be in each orbit, okay, considering the degeneracy. So, that way, so this will be the distribution or density of states. In general, one can write this is the density of states. Okay. Even it is T equal to 0, this will be valid. When T is not equal to 0, then also it is valid. Okay. So, in general, this is the density of states. One can write. So, I am writing in terms of Z, okay, ZE, okay, equal to DE and FE. Okay. So, these are in general density of states for any temperature. Okay. And this dE, that is only valid for T equal to 0. So, I think let us calculate something, okay, using this density of states. Let us be familiar with this. So, if I want to calculate, say, if I want to calculate the Fermi energy at T equal to 0. So, here we are considering T equal to 0. So, just using this density of states, how to calculate. So, that is just to show you I am calculating. So, here Fermi energy I want to find out, right. So, one thing is very clear to us, that number of particles are constant in the system. So, if I integrate this density of states, so 0 to infinity, energy 0 to infinity, 0 to infinity. Okay. So, then it will give me all states that will be equal to the total our that will accommodate our all electrons. So, some states will be occupied, some states will be unoccupied, some states will be maybe partially occupied, whatever. So, in general if we consider, so I can write this density of states, what is this? Number of states per unit energy. So, if I integrate with respect to E energy, so I can write this, right. So, from here I can, so how to proceed? So, this fine density of states, now I integrate over the energy. So, all energy I have considered 0 to infinity, that also there is no problem. Now, I want to find out Fermi energy at t equal to 0. So, under this condition I can say that, so this I can write 0 to infinity, Z is dE and Fe, right, and dE. So, D is this, okay. D is this. Now, here I can consider that since t equal to 0, so I can, this integration I can take into two parts. One is 0 to Fermi energy, because I know at t equal to 0 up to Fermi energy all electrons are filled up, and outside Fermi, above Fermi energy, so they are empty. So, here I can write dE and this Fe is there, fine, keep it, and then plus I can break it. So, Ef to infinity, right, 0 to Ef and then Ef to infinity. Okay. So, at t equal to 0, so there I should write dE Fe dE, right, Fe dE. Now, this distribution, Fermi Dirac distribution, it is telling me at t equal to 0, within this Fermi energy, Fermi level, so this will be 1. When E is less than Ef, so this is 1, I have shown you, and this is 0, this part is 0. Okay. So, this is 0 means this integration will vanish, and this I can remove this one, right, and here I have to replace this dE by d by this, here this part is say constant, only e to the first, so some constant, so some constant, so that is this I will write later on. So, here I have to integrate half e to the power half, right. So, this and d is there, so it will give me what it will give me, this integration will give me this constant equal to constant into 2 this 1 3 by 2 e to the power 3 by 2, right. After integration I will get this. this constant is this, right. Now 2 by 3 multiplied 3 by 2 multiplied, I think it would be, because 2 by 3, because e to the power 3 by 2 divided by 3 by 2. So, 2 by 3. So, 2 by 3 multiplied. So, 2 will go. So, it will be 3 v by 3 pi square, and here e to the power e to the power 3 by 2, e to the power 3 by 2. So, e to the power 3 by 2. Okay. So, basically this density from here, this one I am getting 2 m by h cross square, then v by 3 pi square, v by 3 pi square, v by 3 pi square, and then I have this e 3 by 2, right. And if I put this limit, so this e will be E f, this e will be E f, and this e will be E f. So, you see n equal to exactly I got, n equal to exactly I got, where n I have written well. So, I wrote, but I have removed it. So, from there, so this is n, right. So, this is n. So, now you can see that you can write E f 3 by 2 equal to h cross square by 2 m, right, 3 pi square by v. Now, n is there. So, this n I can write n. Okay. So, I was writing in this form. So, I will write in this form. Well, now this will be 2 by, so 3 by 2, I remove. So, this will be 2 by 3, or whole things will be 2 by 3, yes, 2 by 3. E f, sorry, I did mistake again, n equal to 2 m h cross square v by 3 pi square E f 3 by 2. Okay, so yeah. So, here already 3 by 2 is there. So, that I have not written. So, that is why problem was coming. Okay. So, 3 by 2 I have not written, that is why problem was coming. So, here 3 by 2 was there. So, it will be this, and here v 3 pi square. So, 3 pi square by v n was there. So, that will have 2 by 3. Okay. So, exactly it is same, you see, E f to h cross square by 2 m 3 pi square n by v 2 by 3. Okay. So, just this is the way one can calculate all things. So, thus it is very general method, density of states is using density of states is very general method, and one can calculate everything from density of states. So, this is the one example. Another example I can tell you that if I want to find out the, so I am doing the simplest case just to make you familiar with the with how to use the density of states. Okay. So, now if I find out the average energy of particles or electrons, okay, in our system, average energy of electrons. So, in that case, so in our free electron system, it is only kinetic energy, right. It is only kinetic energy. So, average kinetic energy of free electron system, our system, if we want to calculate at t equal to 0, so these are simpler, that is why I am calculating. So, again I have to define. So, this is the density of states, right. This is the density of state, general density of states. Now, so if I integrate this one, so it gives the total number of integrates from 0 to infinity energy, it gives the total number of electrons in the system. So, now I have to find out the total energy of all electrons. Okay. They are staying in different energy levels. So, each one is having different energy. So, I have to sum up, that means I have to integrate, right. So, I have to integrate. So, I have to take energy, right, energy for this number of states for a particular energy E, right, and integrate over this dE. So, from 0 to infinity. So, this will give me the total energy of the system or free electron system having n electrons, right. Now, I will divide by 1 by n, right, because in this energy range I know 0 to infinity our total number of electrons is n, that I know, okay. Already I have calculated. Now, this then I can write this will be the average energy of our each electron, okay, average energy of our each electron. So, then I have to integrate. So, integration is similar, only one E is there, additional E is there. So, here whatever this from this distribution E half was coming, now another E is there. So, it will be 3 by 2, right, it will be 3 by 2. Okay. Now, integrate. So, everything will be fine, only here 5 by 2, it will be 5 by 2, and it will be 2 by 5, right, it will be 2 by 5. So, this with this basically I can multiply, what I can multiply? I can multiply with earlier it was 2 by 3 and considering 2 by 3 it was coming. Now, I am multiplying 2 by 5. So, here basically so I have to it's okay. I think I should do that. So, it is now 2 by 3. So, then it is not n, it is E0 average. So, E0 average what I will get? E0 average I will get so integration will be similar, 0 to infinity I breaks it 0 to EF and then another EF to infinity, because at t equal to 0 that Fe will control that one, because this EF to infinity, that integration will vanish, because function of E that is 0 for that case, and below this Fermi level it is 1. Okay. So, this is constant, this constant, and then this will be F 5, and then from there this constant is there. So, I can write E 0, I think E 0 bar equal to constant is, what is this constant? Constant is 2 m by h cross square 3 by 2, right, v by 3 pi square, v by 3 pi square. So, that is the constant E, that term we have included here, and into 2 by 5 into 2 by 5 into 2 by 5 e to the power E f 5 by 2. Okay. So, this will be the average energy of each electron. So, yeah. So, for this if I put one thing is missing here, this 1 by n that I have not considered. Okay. So, here this constant by n I have to write, right, this constant by n I have to write. Okay. So, this constant by n, so 1 n will be there, 1 n will come here. Okay. 1 by n. Okay. So, this will be the form. So, this I think E f is h cross square 2 by m, that is fine. So, whether I can make it more simplified. So, if we put this value of n, but unfortunately it is not there, value of n, what is the value of n? Value of n is E f 2 m by h cross square 3 by 2, 2 m by h cross square 3 by 2. Okay. So, n is coming divided by this. So, this term and this term will be same. So, this, so I am putting the value of n. Okay. So, let me do explicitly, otherwise I can do mistake. So, this n equal to h 2 m by h cross square, okay, into E f. Okay. So, this part then 3 by 2, this also 3 by 2, this also 3 by 2, and then now it is removed. So, 3 pi square by v. So, it will be v by 3 pi square, v by 3 pi square. Okay. So, from here what we are getting equal to, so this will go, this will go. So, 2 by 5 will be there, 2 by 5, and then I will get E f, 3 by 2, E f 5 by 2, E f. Okay. So, this is also very important expression, that average energy of the electrons, free electron gas. So, it is at absolute temperature T equal to 0, it is 2/5 of Fermi energy. Whatever Fermi energy, so average energy will be 2/5 of that Fermi energy. So, this also it is, I did mistake in here, it is telling 3/5, my, no, I think it is 2/5, that is okay. So, 2/5 of the free electron Fermi energy. Okay. So, this way one can use the density of states and calculate everything, So, that is why in solid state physics density of states is very important. If you know the density of states, how it is related with the energy, density of states, how it is related with the energy, means energy means at different energy what is the number of density, what is the number of states, and if you know the relation how it is varies. So, that if you know for this particular system you can calculate everything. Okay. So, as you remember that whatever so far we have done, so everything just to develop the quantum theory. Okay. This is the mathematics, and we are getting some expression, everything just the method in quantum theory we use, and now our main purpose is for doing this, main purpose is, what is the main purpose? That free electron theory, basically classical theory, it could not explain thermal heat capacity, it could not explain heat capacity, right, capacity. It could not explain the paramagnetic susceptibility, right. So, this is our, so whatever theory we have developed using that one, whether we can now explain the experimental result. What was the experimental result? I think I need space. So, I remove these things. So, this heat capacity for using classical theory basically use the Maxwell-Boltzmann statistics, Maxwell-Boltzmann distribution. So, that was the mistake basically. So, one has to, for electron system, one has to Fermi-Dirac statistics. So, classical concept and quantum concept, here this main part is this distribution, whether it is following the Maxwell-Boltzmann distribution or Fermi-Dirac distribution. Okay. So, in classical theory, that is Maxwell-Boltzmann distribution was considered. So, heat capacity, what is the heat capacity? To increase unit temperature, what amount of heat we require, right. So, when we give heat to a system, when it is temperature change by T, so then classically we have seen that because this free electron, it will have only kinetic energy. So, each electron will have kinetic energy 3 by 2 kBT, right, 3 by 2 kBT. So, that was the classically it tells that or this kinetic theory, from kinetic theory, that is the standard result. So, that was applied for free electron gas, it is as if that is gas, it's behave as gas particle behaves. So, it will have this 3 by 2 kBT, this energy, kinetic energy, thermal energy basically. Now, how many electrons are there? N number of electrons are there, right. So, I will multiply with n. So, total energy, so each electron will have this, will gain this energy. So, total energy gained by this system is this. okay, or we need this amount of energy to increase by this temperature T, right. So, so that is the energy we need to increase by temperature T. So, dE by dt, that is basically heat capacity C, and if you take specific amount of material 1 mole or so molar specific heat or per gram, if you calculate the specific heat. So, in general it is heat capacity. So, this C equal to dE by dt equal to this, right, 3 by 2 n kb. If you take 1 gram mole, right, 1 gram mole material, so it will have Avogadro number of atoms. So, generally metal atom, it is seen that on the average it contribute 1 electron in free gas, okay, in free electron 1 electron per atom we get as a free electron. So, then it will be Na Avogadro number. So, this 3 by 2 R, right, gas constant. So, this gas constant, this R is 2 calorie, right. So, it gives 3 calorie, right, per gram per temperature, that is there. Okay. Now, you remember that for Dulong-Petit law, okay. So, this specific heat basically in case of material, specific heat is basically 3 R, it is around 6 calorie, right. So, that is that for any material this is seen, okay. And here whatever here we have considered, that is for contribution from electrons. So, in case of metal, whatever specific heat or heat capacity I will see compared to the insulator, if I take insulator it will not have any free electron. So, electronic contribution will in specific heat will be 0, okay. So, that will be only this contribution, sorry, it will be 6 Kelvin, only this contribution. Now, if I take metal, so I will have this contribution, okay, this that is there. Additionally, I should get this confusing. Additionally, I will get this one. So, for metal it should be 50% higher than the insulator heat capacity, right. But experimentally it is seen that it's very small contribution of free electrons in specific heat. It's whatever here we are generally getting. So, it's 1/100th of this one, 1/100th of this value is generally experimentally seen, and also it is seen that it is in this case it is independent of temperature, but for experimental it is seen it is not independent of temperature, it depend on temperature. Okay. So, that classically we cannot explain that one. So, from here we can explain, because you see problem is here, problem is this n is I told that classically it is considered that all electron will have the energy, right, but quantum from here, as I mentioned this statistics, it is telling that when you will increase temperature, so this distribution that was telling, so it is, so depending on this temperature, so that will be kBT energy, and that energy depending on T, so it will remove the electron from near the Fermi energy. So, it will not affect the other electron. So, only this part of electron because of this temperature will get kinetic energy, right. So, this compared to, so this we compare generally with Fermi energy. As I mentioned that this temperature KT and for Fermi energy kBTF, right. So, this with compared to these temperatures, this temperature whether it is small, how small it is, etcetera, depending on that one can get from here that this ratio T by Tf, that will tell you it will give the fraction of the electrons, total electron n will have the kinetic energy. Okay. So, generally this factor we use. So, here, so it is not this many, not all electron, only this into this fraction. So, this the number of electrons will get kinetic energy, will get thermally excited. Okay. So, here whatever C we are getting, whatever C here we have calculated. Okay. So, with that here I am getting additionally T by F, that is because of this distribution, and only electrons near the Fermi energy, Fermi surface, it will be excited. Okay. So, here I am getting this C. Now, it depends on temperature, right. It depends on temperature T, and also this value whatever I got, now it is T by Tf, it is T by Tf. So, this is very small, right. Generally, if in case of room temperature, if T is room temperature and this for generally typical Fermi energy, that is say 3 electron volt, if it is 3 electron volt. So, this temperature is 3000, more than 3000. Okay. So, 300 divided by 3000. Okay. So, it is a just small fraction of the total contribution, classical contribution. So, that is why this value electronic contribution in this heat capacity will be very, very small, as well as it will depend on temperature. Okay. So, these are just phenomenologically, qualitatively I explain you, but using this density of states one can calculate and get the correct factor. Okay. So, this dependence will come, this part will come, only this factor slightly it will be modified. So, that value I can tell you exactly half pi square, if you use this density of states. So, this C it comes half pi square P B, all other things same, T by Tf. Okay. So, just this factor 3 by 2 factor is slightly modified. It is around 9, but it is 4.5, here it is 1.5, it is 4.5. Anyway, this factor is there, but using this density of states exactly you can get the get this result, which main fact is this factor is very small and it depends on temperature. Okay. So, similarly paramagnetic susceptibility also I can show you. As I told, classically it is not explained, but using this quantum theory we can explain exactly whatever experimentally found. Okay. So, but now I will not do that. When I will teach you magnetism, so that time I will teach you. Okay. So, I will stop here. Thank you for your attention.